When 15 supernovae go off close together, both in time and proximity, it makes quite a bang. It should be of no surprise that such a violent event should fundamentally transform the region of space around where it occurred. Interstellar dust was swept aside from the forces of those concurrent blasts, creating a monumental void of low-density matter, and a shockwave that continues to hurtle across the galaxy to this day at a rate of 6 kilometers a second. In its wake, plasma reaching 1 million degrees Celsius in temperature. This simultaneous Swiss cheesing and heating up of the interstellar medium is what is now called a hot bubble, and represents both the end of stars and their beginning. But this is not some distant structure that lurks in a faraway corner of the universe. Our solar system isn't even heading right towards it. We're in it, charging for its point of origin head first. Welcome to our local hot bubble. What scientists now realize is the local environment that exists around our solar system. It is a neighborhood we are still exploring, but its nature is becoming clearer and clearer. So what do we know about the local hot bubble? How did it form? And what more is there to be discovered? I'm Alex McColgan and you're watching Astrum. Join me today as we walk in the aftermath of exploding stars and discuss how scientists even determined we were in the heart of a cataclysm to begin with. The local hot bubble was not always something we knew about. First identified in the 1970s from observations of low-energy X-ray emissions that were detected over the entire sky, the local hot bubble was hypothesized to be a large cavity in the interstellar medium, called a superbubble, filled with tenuous, million-degree, low-density gas. In the 1990s, scientists found that X-ray emissions could happen anywhere neutral atoms interacted with the solar wind, challenging the idea that the emissions must point to a large hot bubble. But soon, evidence would reveal that the hypothesis from decades earlier was indeed correct. In 2014, NASA confirmed the existence of the LHB through the diffuse X-ray emission from the Local Galaxy mission, known as DXL. While soft background radiation can come from other sources, like from comets for example, the mission found that only 40% of the fog of low-energy X-rays came from within our solar system. This affirmed that the dominant source was diffuse X-ray emissions emanating from the million-degree region of interstellar plasma, known as the LHB. Although this confirmed the bubble, questions remained about what could create such a massive void, and what might explain the thousands of surrounding young stars. The prevailing answer proved to be both violent and fascinating. Recent research suggests that the local hot bubble was the aftermath of around 15 supernova explosions that occurred sequentially within a span of a few million years, erupting in relatively close proximity to one another. Scientists estimated that the first of these massive stellar explosions went off roughly 14 million years ago, each expelling enormous amounts of energy, pushing out the surrounding interstellar material and heating the remaining gas to extreme temperatures. Evidence of these ancient explosions has been preserved in our Earth's geological record in deep-sea sediment deposits in the form of a special isotope called iron-60. This radioactive isotope can come from a few different sources, but the most common source of iron-60 is believed to be supernova explosions. We know that the source of the isotope is extraterrestrial because the Earth itself has no way of producing iron-60 on its own, and matching deposits have been found on the Moon as well. The reason that this radioactive isotope is special is because we know how long its half-life is. We know that it decays into cobalt-60, another radioactive isotope, before it finally decays into nickel-60, a stable element. Iron-60 has a half-life of 2.6 million years, and cobalt-60 has a fairly short half-life of just 5.3 years. Because of this, when we find a deposit that contains these elements, scientists can compare the amounts of iron-60, cobalt-60, and nickel-60 like an elemental clock to reveal when that material was deposited on our planet. And luckily for us, international research teams have found several such deposits over the last couple of decades. In 2016, iron-60 deposits were found in deep-sea crust samples taken from the Pacific, Indian, and Atlantic Oceans, indicating two distinct spikes in the radioactive debris that pointed to several supernova events in the not-so-distant past, and not too far from our solar system, just 326 light-years away. The sample showed a spike of iron-60 between 3.2 and 1.7 million years ago, and another spike between 6.5 and 8.7 million years ago. Nuclear physicist Anton Wallner, who led one of these research teams studying the deposits, said that the fact that the more recent debris was spread across 1.5 million years suggests that there were a series of supernovae that occurred one after another in close succession. Astrophysicist Dieter Breitschwert, who led a second team of scientists, identified a likely source of these supernova explosions, which would have occurred 196 to 423 light-years from the Sun. These supernovae that created our local hot bubble may have been part of an aging star cluster, whose surviving members are now associated with the Scorpius Centauri stellar group. Using the iron-60 deposits, the team was able to trace the signals of two supernovae, one that happened 1.5 million years ago and the other 2.3 million years ago, as the result of the deaths of stars that were 8.8 times and 9.2 times the mass of our Sun, respectively. In fact, our LHB is still growing today, albeit much more slowly than when the supernovae exploded millions of years ago. The speed of expansion has plateaued at about 6 kilometers per second now, according to astrophysicist Katherine Zucker. In 2022, Zucker authored a groundbreaking paper that reconstructed the evolution of our galactic neighborhood, tracing the chain of events that created our local hot bubble and led to the formation of all the young stars we see nearby today. From there, they made an incredible discovery. Using data from the European Space Agency's Gaia telescope, Zucker and her team were able to construct a 3D space-time map, showing that within 500 light-years of our planet, all of the young stars and star-forming regions reside on the surface of our local hot bubble. With these 3D positions and the 3D motions of the stellar clusters, they traced back 20 million years of star formation history near our local hot bubble. The implications were clear, that all of the well-known star-forming regions near our solar system had formed along the outer edge of the local bubble as it swept up gas during its expansion. Stellar nurseries are a field we're learning more about all the time, particularly as new images are taken by our telescopes. Here's a spectacular image of the Chameleon 1 dark cloud, one of our nearest stellar nurseries, taken by a dark energy camera on the Victor M. Blanco 4-meter telescope at Cerro Tololo Inter-American Observatory. By studying the propagation of starlight from within it, scientists can tease out details about how stars form, which might help us better understand the local hot bubble's impact on our galaxy today. You might not have seen this particular image before, as new space news is coming out all the time, but I've talked about it in my newsletter, which I've recently launched to help you keep up with all the breathtaking photos released by our many telescopes on Earth and in orbit, or new breakthroughs that reshape how we understand the cosmos. You should sign up to never miss the most exciting news, even if the headlines do, by following the link in the description below. There are new editions that come out every Thursday. From the local hot bubble's birth 14 million years ago, Zucker and her colleagues identified 4 epochs of star formation on the bubble shell. Starting about 16 million years ago, we see the birth of the Upper Centaurus Lupus, or the UCL star cluster, followed by the Lower Centaurus Crux, or LCC star cluster. These formed about 49 light years apart from one another, and about 14 million years ago, these stellar populations were the source of the stars that went supernova to create our local bubble. About 10 million years ago, we see the first of the 4 star-forming epochs after the formation of the LHB. The Upper Scorpius Association and older Ophiuchus stellar populations are born in the first epoch. 6 million years ago, the second star-forming epoch formed Corona Australis and the older stars of Taurus. Then, around 2 million years ago, the stars in Lupus and Chameleon, as well as younger stellar populations of Taurus and Ophiuchus, came to be in the third epoch. And finally, our present time falls within the 4th star-forming epoch. We can observe the dense star-forming molecular gas that surrounds the LHB, which will eventually lead to more star clusters being born along the bubble's outer edge. With all of this stellar creation, you might be surprised to learn that we are interlopers. Our sun did not form inside the local bubble. In fact, the sun was about 978 light years away when the first supernova went off in UCL and LCC, only joining up with the LHB about 5 million years ago as its path through the galaxy took it into the bubble. With the trajectory shown in yellow dots, you can see our sun's location just before it entered the bubble. And now, just by coincidence, our sun happens to be located near the center of the LHB. Drifting into the heart of what was once a raging furnace, scientists became interested in mapping out the ongoing temperature within the local bubble. You might wonder why we're so calm, if temperatures of plasma here can reach 1 million degrees Celsius. The key lies in that plasma's density. Look, this 3D map from Zucker's 2022 publication shows our local hot bubble in dark blue. The density inside our bubble is extraordinarily low, containing about 100 times less hydrogen than the typical interstellar medium. So, while the temperature of this gas soars to around 1 million degrees Kelvin, giving rise to the diffuse X-ray emissions we have observed around the whole sky, we don't have much to worry about. Tracking temperatures within the local bubble has provided more evidence of its existence. The Extended Röntgen Survey with an imaging telescope array, better known as the eROSISTA X-ray telescope, has been able to gather the most detailed all-sky survey of soft X-rays to date, and that data has been used to map the LHB and our solar neighborhood in much more detail than before. Launched aboard the joint Russian and German mission Spektrum Röntgen Gamma, or SPECTRE-RG, in 2019, data from the eROSITA X-ray telescope has allowed a team of scientists led by the Max Planck Institute for Extraterrestrial Physics to create a 3D map of the LHB and identify a temperature gradient where the galactic south was slightly hotter than the galactic north. This temperature dichotomy could be explained by supernova explosions in the past few million years. And by creating this bubble map, the team also found that the LHB is stretched out towards the poles of the galactic hemisphere. This is because the hot gas in the bubble expands out in the direction with the least resistance, which happens to be away from the Milky Way's galactic disk. Along with identifying temperature variations and the shape of the bubble, the team compiled this and other data to create an even more detailed map of our galactic neighborhood. In the new 3D map, our local hot bubble looks like a 3-dimensional splatter surrounded by and even overlapping other galactic structures. These other structures represent known supernova remnants like the Gum Nebula shown here in red, and dense molecular clouds shown here in orange. With the new data and 3D maps, these superbubbles seem likely to be common in our galaxy, creating a Milky Way that's sort of like Swiss cheese. The cavities of our Swiss cheese galaxy are blasted out by gigantic supernova explosions, with new stars forming along the edges of the holes created by dying stars. And, like Swiss cheese, it appears that some of these superbubbles may have tunnels connecting them to other bubbles or other structures, suggesting our local hot bubble could be part of an intricate network of similar features throughout our galaxy. For example, we have the Canis Majoris tunnel, which lies on the Milky Way's galactic disk, and is believed to connect our local hot bubble to the Gum Nebula or another larger nearby superbubble. But the 3D map also revealed another, previously unknown interstellar tunnel, stretching towards the constellation Centaurus, possibly connecting our local bubble to the neighbouring Loop 1 superbubble. While these interstellar tunnels are tantalizing, our current understanding of them is limited. Nevertheless, these tunnels of hot gas and bubbles of star formation shaped by the death of gigantic older stars has me in awe of how powerful and interconnected the evolution of our local galactic neighbourhood really is. It suggests that stars are not just born and die in isolation, but that their energetic output continues to mould the environment for millions of years after their demise. And as our observational tools become more sophisticated, we are beginning to uncover the extent of these hidden structures. So next time you look up at the night sky, you might remind yourself that we are surrounded by crazy patterns, just like our local bubble in the Milky Way that was carved out by ancient cataclysms, and that some of those stars that you see are actually plastered along the walls of a supernova blasted cavity, which connects to other parts of the galaxy through interstellar tunnels. Wow. Imagine for a moment that you're looking out your window when a singular, bright light suddenly flares into existence in the sky above you. This dazzling star is as luminous as the full moon at night, perhaps brighter, and is even visible during the day. If you can see the light, you might already be in trouble, as that unexpected star is now flooding the atmosphere of the Earth with a catastrophic dose of gamma radiation and X-rays, stripping away our ozone layer and exposing us to the full fury of the sun's deadly radiation. And on its way, jettisoned out at 10,000 to 40,000 kilometers per second, a cataclysmic wave of stellar matter and debris hurtles towards our planet, the dying roar of an exploding star venting billions of tons of burning mass at us, ready to sweep across our planet's surface in a tidal wave of fire. This is a supernova. Or at least, it's one interpretation of what we might see if one were to occur near us. But how likely is it for this to actually happen? What constitutes near us on a cosmic scale? How close would a supernova blast have to be before life on Earth would be threatened? What might we on Earth actually experience? And what stars near us have the potential to detonate in this way? I'm Alex McColgan and you're watching Astrum. Join with me today as I discuss an event that could be an Armageddon in our lifetimes, or could be nothing more than a pretty twinkle in the sky. Let's start with the good news. Supernovae in our galaxy are not that common. While astronomers observe hundreds of supernovae every year outside our galaxy, this is mostly a reflection on how many galaxies there are in the universe. Closer to home though, within our own Milky Way, we likely only see about 2 to 3 every century. This means that the odds of one going off tomorrow are not that high. But they're not impossible, and according to archaeologists, the Earth has likely been hit by a supernova before in the course of its 4.5 billion years of existence. For starters, We exist in an area of space known as the local bubble, a relatively sparsely populated region of interstellar space about 1,000 light years across that is thought to have been carved out by a supernova detonation 10 to 20 million years ago, which our planet would have been around for. I talk about that in another of my videos, which you can see here. Scientists have found evidence of another detonation that happened 2.5 million years ago due to a high concentration of iron-60 and manganese-53 in a particular layer of the geological record. This supernova happened far enough away to be harmless to us, but this might not always be the case. There are some scientists who believe that the extinction of woolly mammoths was caused by a massive piece of debris from a supernova crashing into the planet about 13,000 years ago. The impact site in question had magnetic spherules and radioactive potassium-40, a substance found in supernova ejecta. A smoking gun in the era most mammoths went extinct. Even before that, mammoth tusks from 34,000 years ago were found containing tiny impact craters from grains of slightly radioactive iron that had been traveling at 10,000 kilometers per second. If you can recall, that was one of the potential speeds supernova explosions travel at. That can't have been a nice experience for the mammoths in question. An astute observer from this might be able to note an important fact, however. Evidently, if life began on Earth about 3.7 billion years ago, and we faced 3 supernova explosions that have impacted us in the last 20 million years, and life is still largely ticking along, my condolences, woolly mammoths, if you did die out from one of these, then supernovae as a whole can't be quite as destructive as my opening introduction made them out to be. And that's largely true, although it is, of course, a question of proximity. If I'm 1,000 kilometers away from a nuke going off, I have little to fear. But it's a different story if one detonates on my coffee table. And when it comes to supernovae, it turns out that the universe has relatively large coffee tables. To understand the scale of these explosions, it's necessary to understand the forces involved, which means we need to understand a little better about how supernovae happen. It turns out that there's 2 main paths stars can take to get to that explosive grand finale, although in each case it has to be the right kind of star. For the first path, resulting in a Type 1a supernova, it usually needs to be a white dwarf in a binary system that's gradually or speedily siphoning matter away from its neighbouring star until it reaches a point of critical mass. This path is not fully understood, but it's thought that a white dwarf, or a dense star comprising of mostly carbon in a giant superdiamond core, is normally finely balanced between 2 powerful opposing forces: electron degeneracy pressure and gravity. This simply means that atoms usually object to being squashed too much. Their electrons like to remain at certain distances from the nucleus of the atom and will resist being pushed denser than this point. But gravity is an incredibly powerful force that seeks to draw matter closer, particularly in a dense mass like a white dwarf, where a section the size of a sugar cube has the mass of around a car. And in a binary system where the white dwarf is absorbing more and more matter from its neighbouring star, eventually gravity overwhelms electron degeneracy pressure and the whole house of cards collapses at once. Carbon fusion begins. Within a few seconds, most of the star undergoes fusion, forming into heavier elements and releasing a whole lot of energy as the matter in the star settles into its slightly more efficient new configuration. How much energy? Around 1/4 decillion joules. That's 1 followed by 45 zeros. If you claim you knew that number before, you're almost certainly a liar. All of this energy is released in just a few seconds. So naturally, the star ejects its entire contents out in all directions, sending it traveling at 6% the speed of light and unleashing a flood of mostly gamma radiation out across the galaxy. The brightness of this event is 5 billion times brighter than our sun and burns for a few weeks until the ejector has traveled far enough that the overall energy level has started to dissipate. The second type of supernova, type 2, is similar, except instead of involving a white dwarf, it involves a massive star at least 5 times more massive than the Sun at the end of its lifetime. These stars are still burning brightly, and rather than just electron degeneracy pressure, it's also the heat of fusion that keeps the star in balance. However, just like a Type 1a supernova, eventually, balance collapses. This time is because the star runs out of fuel, and without this additional fusion energy pushing the star's mass outwards, electron degeneracy pressure on its own can't cope with the star's weight to similar effect. The only difference is that while some of a massive star will remain, often collapsing down into a neutron star or a black hole, white dwarfs usually vanish completely. Either way, the scale of material and energy released by a supernova is vast. So vast that unsurprisingly, anything immediately next to it is not going to last long. This is an energy powerful enough to rip apart a star. A planet is going to have no chance if it's in the immediate vicinity. Our own sun, thankfully, will never go supernova as it's not massive enough, but if it did, there is a good chance the Earth would be either partially or completely vaporized, its rocky exterior reaching a boiling point thanks to temperatures 15 times hotter than the surface of our Sun, and being whisked away in the weeks of the supernova's passing. What is surprising, however, is how quickly this first wave of devastation would dissipate with distance. Indeed, vaporization is realistically not the largest threat a supernova poses. In 2011, experts from the University of Cambridge calculated that even planets orbiting their star at a distance of 15 billion kilometers, or about 100 times the distance between the Sun and the Earth, would remain intact and would instead simply be sent flying out into space now that there was nothing much left to orbit. Of course, such a planet's hypothetical ecosystem would probably have different problems to worry about. Things would get very cold very quickly. Of course, even if the crust of a planet itself remained intact, that doesn't mean that life on said planet would be sustainable. Ignoring the light of a supernova outperforming the brightness of an entire galaxy sometimes, leading to blindness for anyone who saw it, simply stripping away our atmosphere would carry problems. High levels of radiation, even if it didn't affect us directly, would alter the chemical composition of our atmosphere, negating our ozone layer, vastly increasing our odds of dying of radiation poisoning, and killing off phytoplankton in the ocean, and causing mass extinctions as the consequences of that worked its way up the food chain. Scientists put this kill zone to be within 25 light years. Beyond that, the fury of a supernova begins to calm, as distance causes it to wear itself out. Although admittedly the asteroid that potentially killed the mammoths came from a supernova that was 250 light years away, if it happened at all, it was likely bad luck. Generally speaking, we wouldn't notice any damage from a supernova this far away. Its radiation levels wouldn't be high enough to cause mass extinctions. By 500 light years, we'd hardly notice the event at all, other than perhaps seeing a brighter star in the sky. Which leaves one important question. Within 300 light years, are there any supernova candidates we need to worry about? Thankfully, scientists are fairly confident that the answer is no. Massive stars are very noticeable, and the only two that are at risk of going supernova are Betelgeuse and Antares. Both of those are more than 400 light years away. White dwarfs are a little trickier thanks to their diminished brightness. They've been conventionally hard to spot, making it harder to predict whether we might be at risk from them. However, in 2013, ESA's Gaia Space Observatory released a massive packet of information in its efforts to map the stars that allowed scientists to identify 13,000 white dwarf stars within 326 light years of us. Thankfully, in spite of this large number, scientists remain confident that none of these are scheduled to explode anytime soon. Soon meaning within the next few 100,000 years. Speaking of Betelgeuse, there are some scientists who predict that this red giant might detonate much sooner than that, perhaps within the next few decades. Their research works under the assumption that Betelgeuse has a much larger radius than previously predicted, but if it's true, it might mean that we would get to see a local supernova within our lifetimes. Of course, according to some models, we would have nothing to worry about. The shockwave travelling out from Betelgeuse would take some time to get to us, and even once it arrived, it would be travelling with less force than the push of the solar wind. In other words, it wouldn't be our magnetosphere or atmosphere that kept us safe. The protective sheath of the sun's heliosphere would be enough to keep such a supernova at bay. So, there you have it. While supernovae are perhaps some of the largest explosions in the universe, through some fortunate stroke of luck, our patch of galaxy has nothing really to fear from them. The odds of us being hit by even the neighbouring stars like Betelgeuse that are scheduled to go supernova are incredibly small. True, Earth has plenty of cataclysms of its own, such as floods, earthquakes and hurricanes that can bring devastation to a community in a heartbeat, and space is still a dangerous place. But it's nice to know that of all the things we have to worry about, we can probably cross planetary annihilation from supernovae off our list. The universe is full of secrets, and some of the most incredible ones are hiding just beyond the reach of visible light. What if I told you that more than 1.5 billion unseen objects, from galaxies and newborn stars to some of the oldest stars in our entire galaxy, are sitting just out of reach of us, cloaked in cosmic dust? That's a little frustrating to think about, isn't it? Until now, that is. Because thanks to the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift the veil on these hidden wonders. For the first time in human history, we have a pretty comprehensive infrared map of the Milky Way, one that pierces through the obscuring fog of space to reveal an unprecedented view of our galaxy and what lies beyond. I'm Alex McColgan and you're watching Astrum. Join me today as we appreciate how this first of its kind map was made and take a look at some stunning images that reveal previously unknown stars across our galaxy. In September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever undertaken. Encompassing a 13-year period from 2010 to 2023 across 140 nights of observation, this project has captured around 200,000 images and generated 500 terabytes of data. That's the same amount of data as it would take to stream a 4K video for nearly 3 years straight. VISTA is part of ESO's Paranal Observatory located in Chile, with its main focus being to map large areas of the sky. Using VISTA's infrared camera, known as VIRCam, the team was able to peer through the dust and gas that permeates our galaxy and uncover some of the Milky Way's most hidden places. Traditional telescopes allow us to view space in visible wavelengths, which range between about 380 to 700 nanometers. But VISTA isn't like traditional telescopes. Instead of relying on visible light alone, VISTA operates at infrared wavelengths between 900 and 1200 nanometers, allowing it to detect otherwise invisible objects like stars obscured by dust and cold brown dwarfs, also known as failed stars, which don't emit enough visible light to be seen with a traditional telescope. To get an idea of the difference between visible and infrared light, take a look at these two images of the Lobster Nebula, or NGC 6357, one taken in visible light and the other with VISTA's telescope. We can see that in the infrared, the dust that obscures our field of view seems to disappear, revealing what look like hundreds of thousands, or maybe even millions, of previously invisible stars. The map was created through VISTA variables in the Via Láctea, or VVV survey, Via Láctea being the Latin name for the Milky Way, and its companion project, the VVV Extended Survey, or VVVX. The data collected from these two companion projects that make up the VISTA Infrared Survey have already led to the publication of more than 300 scientific articles. Unlike other recent space maps, this is one of the most detailed ones ever made. It's the first infrared survey to cover nearly 80% of the Milky Way's luminous mass, and provides the largest infrared catalogue ever made of our galaxy's central region. It allows astronomers to study our galaxy in finer detail than ever before. This survey gives us an accurate 3D view of the inner regions of the Milky Way, which were previously hidden by dust. It covers an area of the sky equivalent to 8,600 full moons, and contains about 10 times more objects than any previously published infrared map from 2012. Our Milky Way consists of a central bulge, a dense, bright, puffed up collection of stars, with a flat disk of 2 spiral arms wrapping from the ends. This image shows the area of our galaxy that was mapped in the survey. The red squares mark the central regions of the galaxy, which were observed by the original survey, and then re-observed again by the extended survey. And the other square colors show areas that were only observed as part of the extended survey. From this image, you can see that these surveys have focused right on the central plane of our galaxy, spanning part of the disk and most of the nuclear bulge. But what has VISTA revealed? Argentinian astrophysicist Dante Minniti, who led the survey project, said, "We've made so many discoveries, we have changed the view of our galaxy forever." And as much as I'd love to talk about all of them in this video, it's probably best I stick to some of the highlights. As part of the survey in 2015, VISTA turned its attention to the star formation region of Messier 20, also known as the Trifid Nebula, which lies about 9,000 light-years from Earth. Viewed in visible light in this image, we can see a beautiful nebula, glowing pink from the emission of ionized hydrogen, and surrounded by a blue haze of scattered light from young, hot stars. The cloud of gas and dust is obscuring the star-filled space behind it. Now, look at this second image taken by VISTA's infrared camera. Peering beyond the clouds reveals a whole swarm of new stars. This image not only allows us to see through the Trifid Nebula, but by chance, it revealed objects on the far side of our galaxy that had never been seen before. To their surprise, astronomers identified 2 faint, reddened objects as Cepheid variable stars. While they appear in the image to be just behind the edge of the Trifid Nebula, in reality they are very distant, about 7 times farther than the nebula that once helped to block them from our view. Cepheid variables are a type of bright star that is unstable. They brighten and fade over a period of a few days or a few months, depending on their brightness. The first variable star we ever identified in modern times was Omicron Ceti, also known as Mira. It had been described as a nova until 1638, when Johannes Halwoods observed it getting brighter and dimmer in a cycle that lasted 11 months. As for this pair of newly discovered stars, they are the only Cepheid variables that we have identified so far in this location, which lies beyond the central bulge on the far side of our galaxy. And they can be really useful too. You can think of them as a kind of cosmic yardstick that can be used up to distances of tens of millions of light years. If you know how long the star's pulsation period from bright to dim is, then you can infer its absolute brightness as well as its age. You can compare absolute brightness to the apparent brightness, that is, the amount of light that reaches Earth, so you have a measure of how distant the star is. With a few reference points like these, we can build up a real picture of the scale of our galaxy and beyond. Looking toward the galactic center, a team of astronomers and data scientists found even more candidate Cepheid stars, 655 in fact. They then sorted these into one of two classes, and found that 35 of these 655 stars were classical Cepheids, the younger of the two. This was really exciting, especially since the galactic bulge was thought to contain mostly elderly stars that are at least 8 billion years old. Recording their pulsation periods, the team revealed that all 35 of these Cepheids were less than 100 million years old, and some of them may be as young as 25 million years old. To put that in context, our own sun is about 4.5 billion years old, so the youngest Cepheid has only been around for 0.6% of our sun's lifespan. The team's exploration of Cepheids culminated in another major discovery. By mapping the 35 classical Cepheids they found, the team was able to trace a completely new feature in the Milky Way, a thin disk of young stars that stretches right across the galactic bulge. Buried behind thick clouds, it had remained unknown in all previous surveys of the region. In revealing this structure, combined with the discovery of older Cepheids as I mentioned earlier, scientists have inferred that there has been continuous star formation along the midplane of the galaxy for the past 100 million years. There might also be even younger Cepheids that we haven't seen yet, as these stars would be so bright that they would be saturated in the VVV survey. The fact that we found this thin disk of young stars within the galactic bulge is incredible. We used to think that the galactic bulge was an ancient feature of our galaxy's past, where exclusively old stars had formed separately from the stellar disk. But this finding reveals that things aren't so black and white, and that the formation of newer stars within the bulge could be a natural progression of our galaxy's evolution. But even more inspiring perhaps is a discovery by the VISTA infrared survey that lies at the ancient heart of our Milky Way galaxy. In 2016, for the first time, a type of ancient star known as RR Lyrae, another variable star, was discovered in the center of the Milky Way galaxy by a team led by astrophysicist Dante Meniti and Rodrigo Contreras Ramos. This type of star is usually found in globular clusters, which tend to orbit the outer regions of the galaxy. A globular cluster is a tightly packed group of stars that contains tens of thousands to millions of stars bound together by gravity. They're also really ancient, containing a stellar population that can be over 10 billion years old. The team found 12 RR Lyrae stars during the VVV survey, which suggests that they might be the remnants of an ancient globular cluster right at the heart of our galaxy. This finding also provides evidence that might help astronomers to decide between the two competing theories of how nuclear bulges form. While some scientists think that the nuclear bulge forms early in the galaxy's evolution, when multiple smaller galaxies violently collide, others say that it forms gradually over time, where gas is funneled inwards to trigger star formation. Finding these ancient stars here suggests that the bulging center of the Milky Way likely grew through the merging of primordial globular clusters, therefore supporting the first theory. So not only does it hint at our own galaxy's beginnings, but it also offers compelling evidence into how these galactic bulges might form in other similar galaxies. Speaking of ancient stars, VISTA was able to find 2 new globular clusters as part of the infrared survey in 2011. In this visible light image, a known globular cluster, UKS1, can be seen on the right as a hazy red splotch. This cluster had been the dimmest known globular cluster until the new discoveries. Now, compare this same patch of sky, but this time in VISTA's infrared light. Suddenly, we can see what we have been missing. Much more faint than the known UKS1, we can make out a second globular cluster, this time in the upper left of the image, which has been named VVV-CL001. Another globular cluster, aptly named VVV-CL002, was found soon after, and this small, faint group of stars may be the closest known globular cluster to the center of the Milky Way. Did you know that there were only 158 known globular clusters in the Milky Way before these new ones were found by VISTA? For the survey to identify 2 more of these rare stellar objects is quite a significant accomplishment. Within this central region of the galaxy, it's easy for younger stars and cosmic dust to obscure globular clusters, especially since their age prevents them from shining as brightly. But now that they've been revealed, these features bring exciting possibilities for further study. It could just be an illusion of perspective, but scientists have wondered whether VVV-CL001 is gravitationally bound to UKS1. If this is the case, then they would be the Milky Way's first known binary globular cluster pair. We found binary clusters in other galaxies, like in Centaurus A and the Large Magellanic Cloud, but scientists think it might be when these gravitationally bound clusters collide that we get the most massive globular clusters, like Omega Centauri. So studying a binary cluster right in our own galaxy could produce some amazing insights into this process. It's all speculation at the moment, but it's definitely cool to think about. In addition to globular clusters, the VISTA infrared survey identified a multitude of other types of star clusters. At least 96 new open or galactic clusters have been found, which typically contain fewer, younger stars and are much more common than the globular type. Like the globular clusters, they have been hidden by cosmic dust, but VISTA's 4.1 meter infrared telescope has lifted the curtain to show them in all their glory. Take a look at just a few of these stunning images we now have of these objects. One of these open clusters, VVV-CL003, is much more difficult to make out in images compared to the tightly packed globular clusters. Try and see the density differences in the stars in this section of the image compared to the surrounding regions. It was found by VISTA 15,000 light years beyond the Milky Way center, and also happens to be the first of its kind to be discovered on the far side of the galaxy. The sheer scale of this survey is staggering, covering a vast region of the sky and mapping more than 1.5 billion objects. This data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way and beyond. And that's just the tip of the iceberg. This survey will serve as a foundation for future telescopes and observations, which will hopefully be able to expand on VISTA's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map that has ever been made of the Milky Way structure and objects, one that unveiled hidden wonders previously beyond our reach, and scientists are already uncovering new galactic features and reshaping our understanding of the galaxy. With the information from this groundbreaking infrared survey, as well as the recent work from ESA's Gaia mission in visible light, it's an exciting time to be an astronomer, and we can expect a flurry of new insights about our own galaxy and the universe as a whole. VISTA's infrared observations have unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries where stars are born, and they have broadened our understanding of the formation of our Milky Way. Looking at the sky through different wavelengths has brought about a new era of galactic exploration, and I can't wait to see what else astronomers and data scientists are going to uncover thanks to VISTA's 3D map. Some of you may remember my first video I ever did on my channel, which was how big is our solar system? If the sun was the size of a football or a soccer ball. Today I'm going to do that again, but this time I'm going to scale it down a little bit, where the sun is only the size of 1 millimeter, like a grain of sand. We're going to see how big the solar system is in comparison to the sun being that big. So we'll start off first of all with the sun. I'm going to put it just by here. Now the closest planet to our sun is of course Mercury, and if the sun was 1 millimeter in diameter, that would mean Mercury is 4 centimeters away. So I'm going to put it just by there. There's Mercury. So the next closest planet to the sun is Venus, and it is 8 centimeters away. So there we have Venus. The next one is us on Earth, and that is 10 centimeters away. Then we have Mars, which is 16 centimeters away. The next one we'll mention here is Ceres, a dwarf planet found in the asteroid belt, and that is 30 centimeters away. Okay, the next one is Jupiter, and that is 56 centimeters away. We're getting far away now. Saturn is 1 meter and 3 centimeters away. Coming to the first of the ice giants now, we find Uranus, which is massive, 2 meters and 6 centimeters away. The last real planet in our solar system is Neptune, and that is 3 meters and 24 centimeters away. And then we have Pluto, which is 4 meters and 22 centimeters. And this is the last thing that we'll look at in our solar system. At this point you may be wondering, well, what about the closest star, Alpha Centauri? Well, you're going to have to follow me a little bit, so come on, let's go.
I know this wasn't really a straight line, but yes, Alpha Centauri, if the sun was the size of just 1 millimeter, Alpha Centauri is 30 kilometers away, and that's our closest star.
Thanks for watching. This video was in part made possible by all the Astromnauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.